So hello, this lecture is going to be on the conformation and stability of cycloalkanes, alkanes that have cyclized to form a ring. Since cycloalkanes have carbon-carbon single bond, there is a freedom of rotation across these carbon-carbon single bond. Then as they rotate through their carbon-carbon single bond, they adopt different structures. So the different structures, cycloalkanes or generally alkanes, adopt as the result of freedom of rotations across their carbon-carbon single bond are called conformation. And then these different conformations which cycloalkanes or alkanes adopt have different degrees of stabilities. Some of the conformers are stable while the other conformers are unstable. So what we are going to do in these and the subsequent lectures is to determine the different conformations cycloalkanes adopt and then analyze these conformers in terms of their stability. As a result, we determine the most stable conformers as well as the least stable conformers. These cycloalkanes adopt as a result of rotation across their carbon-carbon single bond. So before I do that, let me just first start by defining what conformation is. So conformation is the various special arrangements available to a molecule by rotation about single bond. That's what is called conformation. As you can see, this is a model of a molecule of ethane, while this one is a model of a molecule of cyclohexane. And then since both of them are alkanes, and since they have carbon-carbon single bonds, there is freedom of rotations across their carbon-carbon single bond. As a result of these rotations, these molecules adopt different conformations, different structures. And then these different structures they adopt have different degrees of stabilities. Some are less stable, others are very stable. So we are going to study about the different conformations cycloalkanes adopt as a result of the rotations across their carbon-carbon single bond. We'll see what these different conformers are, and then we'll determine their stability, and then we'll also determine and understand why some conformers are more stable than the other, what makes a particular cycloalkane to be more stable than another cycloalkane. So before I do that, let me just show you using a model how. So let me demonstrate to you how there is freedom of rotations across carbon-carbon single bonds of open chain alkanes as well as cycloalkanes, and how as the result of this freedom of rotations these molecules adopt different conformations, and why some of the conformations are more stable than the other. So this represents a molecular model of ethane, CH3, and another CH3 carbon, two of these joined to each other through a single bond. So the black in this model represent the two carbons, while the whites represent the 6 hydrogens of ethane. So this is a carbon, and then these are the 3 hydrogens on it, and then this is the other carbon, these are the 3 hydrogens on it, CH3 and CH3. And the 2 carbon atoms are joined to one another through a single bond. The 2 carbon atoms are joined to each other through a sigma bond, which is formed by direct head-on overlap of sp3 hybrid orbitals. One sp3 hybridized carbon and another sp3 hybridized carbon, they approach each other and then they share their electrons through direct head-on overlap of orbitals to form this sigma bond. So if you have a molecule like an alkane that has got only sigma bonds, no pi bonds at all, that means no double bond or triple bond, in such type of molecules there is freedom of rotations across the carbon-carbon single bond. For example, I could hold one of the carbons like this and then rotate this one, okay, and rotate this one. This one freely rotates, and rotations of course start from 0 degrees all the way to 360 degrees. As it rotates, it will adopt different conformations. The spatial relationship between the hydrogens of this carbon and the hydrogens of this carbon changes as the molecule rotates. Then as it does that, it will be adopting different conformations, different structures, okay, different conformational isomers. Now, as it rotates, first let's start here, where this hydrogen is facing this one is also facing this one is also facing this one, and let us rotate it. If we rotate it by 180 degrees, remember in this conformation these two are facing each other like this. If I rotate it by 180 degrees, you'll see that this one will be facing in the opposite direction from this one. This and this one will be very far apart from each other. So initially they were like this. So in this conformation, the two hydrogens are facing directly at each other like this. They are facing at each other directly like this. But in this other conformer, they are very far apart from each other. So in this conformation, called the eclipsed conformation, because the hydrogens are eclipsing each other. This one eclipses this one eclipses the other, okay? If you look at them like this, one is eclipsing the other. Like from your side, probably you can see this one, but you will not see the one behind it. That's what being eclipsed means. So this one is called the eclipsed conformation, while this one is called the staggered conformation. So in the staggered conformation, as you can see all the hydrogens, and the hydrogens on the neighboring carbon atoms are as far away from each other as possible. So when it is in the eclipsed conformation like this, this hydrogen and these hydrogens are very close to each other compared to the staggered conformation. So when it is in the eclipsed conformation, you have these electrons of this carbon-hydrogen bond. And then you have these electrons of the carbon-hydrogen bond. These two electrons of the carbon-hydrogen bond and these two electrons of the carbon-hydrogen bond are very close to each other, unlike when they are in the staggered conformation. So when they are in the eclipsed conformation, these electrons of the carbon-hydrogen bonds are very close to each other. You remember, electrons are, of course, both of them are negatively charged. Like charges repel. As a result of that, there is going to be some kind of strain that will develop in the molecule when these hydrogens face each other or eclipse each other. There is going to be some electrostatic repulsive force between the electrons of this carbon-hydrogen bond and the electrons of the carbon-hydrogen bond, all through this one and this one, this one and this one. As a result of these electrostatic force, repulsive force, this conformer is unstable. So in order to become stable, this molecule will rotate across its carbon-carbon single bond. Then as it rotates through its carbon-carbon single bond, slowly the two hydrogens will continually become apart from each other. They will no more be eclipsing each other, and then there will be a point where this one is facing up while the other one is facing down. This one is facing down, this one is facing up. This conformation is called the staggered conformation. So in the staggered conformation, there is no electrostatic repulsion between the electrons of this carbon-hydrogen bond and the electrons of the other carbon-hydrogen bond. Even these ones are as far away from each other as possible. This is the staggered conformation. So between the two conformations, the staggered conformation is very, very stable, while the eclipsed conformation is the least stable. So alkanes, as the result of freedom of rotations across their carbon-carbon single bond, they can adopt infinite number of conformations, infinite number of conformations that have different degrees of stabilities. The least stable of all this conformation is the eclipsed conformation, where the electrostatic repulsive force between the electrons of this carbon-hydrogen bond and this carbon-hydrogen bond is maximum, and the staggered conformation is the most stable, where the electrostatic repulsive force between the electrons of the corresponding carbon-hydrogen bonds are very far apart from each other. So by rotation across their carbon-carbon single bond, cycloalkanes adopt different conformations. I can assure you, this ethane will not prefer to be like this, to have this conformation. It will prefer to have such a conformation. So this will be the most stable conformation of ethane, while this one is the most unstable conformation of ethane. So this adopt as a result of freedom of rotation across their carbon-carbon single bond. The same also happen to cycloalkanes. Cycloalkanes are the result of rotations across their single bonds, their carbon-carbon single bonds. As a result of rotation, it may not be as free as the case of open chain alkanes, but all the same, they rotate. They rotate. Then by rotating across their carbon-carbon single bonds, they adopt different conformations. And then these different conformations cycloalkanes adopt have different degrees of stability. Some are stable while others are unstable. So in summary, the two extreme conformers of cycloalkanes are the eclipsed conformation and the staggered conformation. In the eclipsed conformation, the two hydrogens on neighboring carbon atoms, they face each other like this, very close to each other. One is eclipsing the other. As the result of that, there is going to be an electrostatic repulsive force between these electrons of the carbon-hydrogen bond. So the eclipse conformation is less stable because electrons repulsion between the electrons of the carbon-hydrogen bond is at maximum. However, in the staggered conformation, the hydrogens of the neighboring carbons are as far away from each other as possible. For example, if this hydrogen is this one, then this hydrogen is the one down here. And then these ones separate themselves by 60 degrees as far away from each other. So this conformation is the staggered conformation. It is more stable. It is the most stable conformation because in the staggered conformation, as we have seen, the electron repulsion is at a minimum. So cycloalkanes adopt different conformations as a result of freedom of rotations across their carbon-carbon single bonds. And the reason why cycloalkanes undergo various conformations, as we shall see, is to become stable. By rotating across their carbon-carbon single bonds, cycloalkanes will adopt conformation in which the eclipsing is at its minimum. The strain that comes in the ring as a result of eclipsing of the hydrogens of the neighboring carbon is at minimum as possible. So we have seen one of the reasons why cycloalkanes rotate across their carbon-carbon single bonds to adopt different conformations. One of the reasons why they adopt these different conformation is in order to become stable by avoiding their eclipsing of their hydrogens. They rotate, say that the eclipsing of the hydrogens on neighboring atoms is at its minimum. Say that the electrostatic repulsive force between the electrons of the carbon-hydrogen bonds in the neighboring carbon atoms is at its minimum. Then, as we shall see, the other reason why cycloalkanes adopt different conformations is to have their bond angle to the ideal 109.5 degrees of sp3 hybridized carbons. So if you look at this, is a molecule of propane. So CH3, CH2, CH3, one carbon here, another carbon here, another carbon here. For purpose of clarity, I decided not to include the two hydrogens in here. I have not drawn them. I have drawn the three hydrogens of this carbon and the three hydrogens of this carbon. So since alkanes are sp3 hybridized, since the carbons of alkanes are sp3 hybridized, their bond angle, any of these bond angles are 109.5 degrees. Of course, we know cycloalkanes are like alkanes. They have carbon-carbon single bonds. The hybridization of the carbons of cycloalkanes is sp3. As a result, we should expect their bond angle to be also 109.5 degrees. Is it possible for the bond angles of cycloalkanes to be 109.5 degrees all the time? Let's take an example of cyclopropane. Is it possible for this bond angle, and these bond angles, is it possible for these bond angles to be 109.5 degrees? Of course not possible. As you can see, this is cyclopropane. All the carbons are sp3 hybridized. All the carbons are bonded to 4 atoms, to the 2 hydrogens and to the other 2 carbon atoms. You should expect, since this carbon is sp3 hybridized, this bond angle must be 109.5 degrees. Of course, it's not possible for the bond angle of a cyclopropane to be 109.5 degrees because the total bond angle, the internal bond angle of a cyclopropane, just like an equilateral triangle, it has to be 180 degrees. Then each of them should be 60 degrees. This is the ideal normal bond angle between the carbon bonds in an alkane, 109.5 degrees. However, when the carbon atoms form part of a ring, what their bond angle will be controlled or determined by the requirement of the ring. There is no way, even if you wish to have a bond angle of 109.5 degrees in a cyclopropane, not possible at all. So the ideal bond angle for an sp3 hybridized carbon is 109.5 degrees, something like this. Even for cycloalkanes, since they are sp3 hybridized, their bond angle should be 109.5 degrees. So the stability of cycloalkanes, in addition to the eclipsing of the hydrogens, is determined by their bond angle. The closer their bond angle is to the ideal 109.5 degrees, the more stable the cycloalkane is. As much as possible, their bond angle should be 109.5 in order to become stable. Let's look at the situation of the bond angles of the different cycloalkanes. Let's look at what the bond angle in cyclopropane, in cyclobutane, in cyclopentane, in cyclohexane, and in cycloheptane is going to be like. What is the dimension of these bond angles? If we assume these cycloalkanes to have the same shape like the regular polygons, it's like cyclopropane is an equilateral triangle, while cyclobutane is a square and cyclopentane is a regular pentagon, while cyclohexane is a regular hexagon and cycloheptane is a regular heptagon. Of course, for regular polygons, we can determine their internal bond angle. Of course, since cyclopropane has 3 carbon-carbon single bonds, and then all these bonds are the same, cyclopropane is like an equilateral triangle. As a result, the internal bond angle in here is 60 degrees. And then when you look at cyclobutane, cyclobutane is like a square. It's a square with all four sides being the same. As a result, all the four angles being the same. So if you calculate the internal angle of a cyclobutane or the bond angle of a cyclobutane, you'll find it is 90 degrees. How about the bond angle in here, or in here? Of course, as regular polygons, for a regular polygon, you can calculate the internal bond angle, using this formula, n minus 2 times 180 divided by n, where n is the number of sides. In a triangle, we have 3 sides. So 3 minus 2 is 1. 1 times 180, 180. 180 divided by 3 is 60. The same for a square. 4 minus 2, 2 times 180, 360. 360 divided by 4, it is 90 degrees. So if we do this calculation similarly, you will find the bond angle of a cyclopentane is 108 degrees, while that of a cyclohexane is 120 degrees, and that of a cycloheptane is 129 degrees. So if we continue like this, that of cyclooctane will be more than 129 degrees, etc. Now, based on their bond angle, you will see that cyclopentane has a bond angle closer to the ideal 109.5 degrees. As a result, based on bond angle, you will see that cyclopentane is the most stable of all the cycloalkanes, because its bond angle is closer to the ideal 109.5 degrees. Let's assume this is 109.5 degrees. It is closer to the ideal 109.5 degrees. And then cyclobutane and cyclopropane are unstable because their bond angle is less than the ideal 109.5 degrees. Their angles are compressed. Instead of being like this, they are forced by bending their orbitals for the bond angle to be reduced. So their orbitals, as we shall see, for cyclopropane and for cyclobutane are bent like this. They are under a lot of strain. There's a lot of angle strain. So cyclobutane and cyclopropane are unstable because of strain of the angle. Their angles are strained, less than the ideal 109.5 degrees. And then in the case of cyclohexane, cycloheptane, and the other larger cycloalkanes, their bond angle is more than the ideal 109.5 degrees. Instead of being like this, instead of their bond angle being like this, they are forced to expand. And these are the orbitals that are separated by 109.5 degrees, the sp3 hybrid orbitals that are separated by 109.5 degrees. Then if you want to increase the bond angle, you have to bend the orbitals outside like this in order to increase the bond. So even these are unstable because of the expansion of their bond angle beyond the ideal 109.5 degrees. So So these angles are determined by assuming that cycloalkanes are like regular polygons, flat planar molecules, where all the carbon atoms being in the same plane. But you remember, cycloalkanes, like alkanes, they have carbon-carbon single bonds. By rotation across their carbon-carbon single bonds, cycloalkanes will adopt different three-dimensional structures. Then one of the purpose of doing this is to bring their bond angle closer to the ideal 109.5 degrees. So based on this, cyclopentane is the most stable, while cyclopropanes and cyclobutanes are unstable because their bond angle is below 108, whereas cyclohexanes and cycloheptanes and the larger cycloalkanes are less stable because their bond angle is greater than 109.5 degrees. How is this observation related to experimental data? If we were to determine the stability of these different cycloalkanes, which one will we find to be the most stable? In order to do this, we can determine the energy that is contained in these cycloalkanes. So we can compare them based on their heat of combustion, the energy that is released from these cycloalkanes as they combust, as they burn. Of course, the more the energy, the less stable they are, because stability is related with low energy. The lower the energy, the more stable a molecule is. Of course, if we measure the heat of combustion of cycloheptane and compared it with cyclopropane, of course the heat of combustion of cycloheptane will be more than the heat of combustion of cyclopropane, because there are more carbons in cycloheptane than there are in cyclopropane. But what is common in all this? What is the empirical formula of all these cycloalkanes is CH2. So we can compare the stability of these different cycloalkanes based on the energy contained in every CH2 of these cycloalkanes by measuring the energy per CH2. For example, you can measure the heat of combustion of cyclopropane, and then whatever value you get, you divide it by 3. So that way you will get the energy contributed by every CH2 of cyclopropane. Similarly, we can measure the heat of combustion of cyclohexane and divide it by 6, because in cyclohexane we have 6 CH2s, a CH2, a CH2 here, a CH2 here, a CH2 here, a CH2 here, a CH2 here. So we divide the heat of combustion by 6, we'll find the energy that is contained in every CH2 of cyclohexane. That way we can compare them. So an experiment was conducted to determine the stability of cycloalkanes based on the energy contained in every CH2 to determine the stability of the cycloalkanes, and this is the finding of the result. So for your information, if you take an open chain alkane like this, that is not cyclized, as a result of the fact that it is free like this, it does not have any strain. So as a result, it is very stable. Then if you calculate the energy per every CH2 of an open chain alkane, it is about 157.4 kilocalorie per mole per every CH2 of an open chain alkane. Heat of combustion for an open chain alkane per CH2 is 157.4 kilocalorie per mole. Now let's compare the energy contained in every CH2 of the different cycloalkanes. So this one is comparing the energy contained per every CH2 of the cycloalkanes, starting from the smallest cycloalkane, cyclopropane, then cyclobutane, cyclopentane, cyclohexane, cycloheptane, cyclooctane, cyclononane, and cyclodecane. So now, when the heat of combustion per every CH2 was determined for cyclopropane, it was found to be 166.6 kilocalories per mole. And then if you look at this, this is the highest number of all, which is consistent with our previous finding, because it is cyclopropane that has got a bond angle that is further away from the ideal 109.5 degrees. So we should expect this one. And then for cyclobutane, the energy per every CH2 is less than that of cyclopropane. It is 164.0, indicating to us cyclobutane is more stable than cyclopropane. This is expected because the bond angle of cyclopropane is 60 degrees, while the bond angle of cyclobutane is 90 degrees. 90 degrees is closer to the ideal 109.5 degrees than 60 degrees is, so it is more stable. And then for cyclopentane, you remember the bond angle of cyclopentane, assuming that cycloalkanes are like regular polygons, the bond angle was 108, which is the most closest to the ideal 109.5 degrees. So based on that, if that was the case, we should expect the heat of combustion per CH2 of cyclopentane to be the lowest, but that's not the case. The cycloalkane that has got the lowest heat of combustion per CH2 is cyclohexane. Then as you go further, as the size of the ring increases, since from the calculation of the internal bond angle, as we have seen previously, the bond angles continue to increase, the instability should increase. They should become more and more unstable. But that's not the case. In fact, cycloheptane is more stable than cyclopentane, and it is not increasing significantly. So what this is telling us, these cycloalkanes are not flat molecules. They are not flat. They adopt a three-dimensional structure through rotations across their carbon-carbon single bond, so that their bond angle can get closer to the ideal 109.5 degrees, as we shall see later. Through rotation across its carbon-carbon single bond, the bond angle, the internal bond angle of cyclohexane is not 120 degrees, but the ideal 109.5 degrees. Okay, so cycloalkanes, by rotating across their carbon-carbon single bonds, they will adopt different types of conformations. And the purpose of this is to become stable. One of the reasons, as we have seen, why cycloalkanes undergo conformational change is to get rid of the strain that comes as a result of the electrostatic repulsion of the two carbon-hydrogen bonds that are on neighboring carbon atoms. Rather than being eclipsed by adopting a three-dimensional structure, somehow they manage to relieve some of this strain. As we shall see, such kind of strain is called torsional strain. One of the reasons they adopt different conformations is to relieve the torsional strain so that they can become stable as much as possible from the eclipsed conformation, where the hydrogens on neighboring carbon atoms face each other, where their electrons repel each other. They rotate so that this one remains up the way it is, while this one comes down. Rotate by 180 degrees like this to the staggered conformation in order to avoid or minimize the electrostatic repulsion so that they can become stable. The other reason why cycloalkanes adopt different conformation is to have their bond angles closer to the ideal 109.5 degrees. One of them is to avoid this strain. This strain is called torsional strain, as I will explain in a short while. To minimize or eliminate torsional strain, the eclipsing of the hydrogens on the neighboring carbons. The other reason why cycloalkanes adopt different conformation is to, as much as possible, bring their bond angle to the ideal 109.5 degrees in order to minimize the strain that comes as a result of formation of a ring to the cycloalkane. So like when the cycloalkane is open like this, there is no strain. But the moment it forms a ring like this, there is going to be strain. The bond angle will not be the ideal 109.5 degrees. There is going to be torsional strain, etc. So there is going to be a strain that comes as a result of formation of a ring. That's why the open chain is very, very stable. But when a ring is formed, as in the case of cyclopropane and cyclobutane, as you can see, they become very, very unstable. They become very strained. The ring becomes very, very strained, very unstable. Easily openable ring. The ring can easily open. The ring can easily break because it is unstable, very highly strained. But through puckering, through adoption of different structures, different conformations, cycloalkanes, as much as possible, minimize this. So as we shall see later, in the case of cyclohexane, all the hydrogens on neighboring carbon atoms are staggered like this, totally eliminating the torsional strain, totally eliminating the electrostatic repulsive force between the electrons of the corresponding carbon-hydrogen bonds, totally eliminated. And their bond angle is ideal 109.5 degrees. Not compressed or expanded. See, you should understand what reducing the bond angle means. These bonds are formed, since they are alkenes, as a result of orbital overlap of their sp3 hybrid orbitals. So the orbitals overlap at 109.5 degrees, like this. This is ideal. These are the same sp3 hybridized orbitals that are in an open chain, which are now being used to form a ring. When they form a ring, as we saw in the case of cyclopropane, the bond angle cannot be 109.5 degrees. This bond angle can only be 60 degrees. So what's going to happen? These orbitals have to bend inwards, this one as well as that one, to the point of almost breaking. That's why they are very, very unstable. Okay, so what this is telling us, what this result and comparison of this result with this is telling us, that cycloalkanes are not flat. They adopt a packed three-dimensional conformation. They change their form. Okay, this lip is changed. It is formed from the normal position to a packed position. So that's what packering means. They adopt a packed three-dimensional conformation. The reason why cycloalkanes adopt a packed three-dimensional conformation is to become stable, to minimize their energy. So cycloalkanes adopt packed three-dimensional conformation in order to minimize energy, to adopt a minimum energy conformation that has minimized or eliminated this eclipsing of the hydrogens on the neighboring carbons, or taking their bond angle to the ideal 109.5 degrees. Now, cycloalkanes adopt their minimum energy or conformation through packering for a combination of three reasons. There are three reasons why cycloalkanes will have a rotation across their carbon-carbon single bonds. Cycloalkanes, through rotations across their carbon-carbon single bonds, adopt different packed conformations. And the reason why they are doing this is for three reasons. One of them is to relieve the angle strain. As we discussed, the ideal bond angle for cycloalkanes, since they are alkanes, since they are sp3 hybridized, it has to be 109.5 degrees. But it's not possible for all cycloalkanes to have this ideal 109.5 degrees. As a result, their angle is strained. One of the reasons why the ring is going to be unstable is because of angle strain. The strain due to expansion or compression of bond angles from the ideal 109.5. Expansion being more than 109.5 degrees and compression being less than 109.5 degrees. So this is probably the ideal 109.5 degrees. And then their bond angles could compress or expand to be more than 109.5 degrees. Whichever the case, it will bring angle strain. So cycloalkanes will adopt their minimum energy conformation in order to minimize or eliminate angle strain. The other reason cycloalkanes will undergo conformational changes or adopt their minimum energy conformation is to get rid of torsional strain. So torsional strain is the strain due to the eclipsing of bonds on neighboring atoms. It is an increase in energy caused by eclipsing interactions. For example, if you look at this cyclopropane, that this hydrogen and this hydrogen, they are eclipsing each other. If you look at this one, they're also eclipsing each other. This one and this one are eclipsing. These ones and these ones are eclipsing. As a result of eclipsing, there is electrostatic repulsive between the electrons of the corresponding carbon-hydrogen bonds. So alkanes will adopt different conformations in order to minimize or eliminate torsional strain. So torsional strain, what you should know, is a strain that comes as a result of eclipsing of hydrogens that are on neighboring atoms like this. This and this eclipse. That's what eclipsing is. Eclipsing. But if you replace the hydrogen, which is the smallest element in the periodic table, with a larger substituent, for example, if I replace, instead of having a hydrogen here, which is the smallest element, and then we have this much distance between this hydrogen and this hydrogen, but if I replace this one with SCH3, which is now a larger group, as you can see, this hydrogen has become very close to it. As a result of this, there is going to be steric strain. Steric strain. So steric strain is the strain due to the repulsive interaction when atoms approach each other too closely. So these ones are as far apart from each other as possible, because this is the smallest element, hydrogen. This is also another hydrogen. Both of them are the smallest element. They are as far away from each other as possible. But when you replace the hydrogens with a bulky group, and then this bulky group will come very close to it, to the other hydrogen, to the other atoms. So as a result of that, there is going to be steric strain. So cycloalkanes will adopt a three-dimensional conformation in order to minimize these steric strain. So by rotating like this, so as you can see, it is now a bit far from these ones, relieving some of the strain that has come as the result of the fact that the substituents are very close. Instead of being like this, now they are like this. When they are like this, there is going to be a much stronger electrostatic repulsive force, which makes the molecule very unstable. So they will adopt a three-dimensional conformation that will allow them to minimize this and eliminate it if possible completely. So cycloalkanes adopt their minimum energy conformation through Packering for a combination of three reasons. One of them is to relieve and get rid of the angle strain by taking their bond angle to the ideal 109.5 degrees. The other reason is to get rid of torsional strain, and this torsional strain is a strain that comes as a result of eclipsing of bonds on neighboring atoms. The bonds of these and the bond of this, they are eclipsing each other. That is torsional strain. So they adopt a three-dimensional conformation through rotation across their carbon-carbon single bond, so that this torsional strain is minimized and finally eliminated as much as possible. The other reason why they adopt their minimum energy conformation is to get rid of the steric strain. So the steric strain, what makes it different from the torsional strain is when you have a bulky substituent on the neighboring atom. This bulky substituent, since it is bigger in size, unlike the hydrogen, which can be this far, this bulky substituent can come very close to it. Then as a result of that, there is going to be a strain that's going to arrive as a result of the proximity of the electrons of the two bonds on the neighboring carbon atoms. There is going to be a lot of strain. In order to avoid this strain, it will be rotating so that this steric strain is removed or minimized. So the strain you see in a particular cycloalkane is a combination of this. So the ring strain of a cycloalkane is the total sum of the above three. All these three contribute towards the stability of the cycloalkane, will determine how strained the cycloalkane is compared to an open chain alkane. So you now know what conformations are. These are the various special arrangements that are available to a molecule by rotation about single bonds. These are what are called conformations. The investigation of the various conformation a cycloalkane adopt and determining their relative stabilities is known as conformational analysis. So in conformational analysis, you determine the various conformations a molecule can adopt, and based on their angle strain, torsional strain, and steric strain, you determine the stability, the relative stabilities of the different conformers, so that you can determine which one is more stable and which one is less stable. This is what is called conformational analysis. Now we are going to look at the conformational analysis of the first four cycloalkanes. We look at the conformational analysis of cyclopropanes, cyclobutanes, cyclopentanes, and cyclohexanes. First, we look at the conformational analysis of the first three cycloalkanes, the ones with 3 to 5 carbons, from cyclopropane all the way to cyclopentane. So we are going to do conformational analysis, or we are going to look at the conformations of the 3 to 5 membered rings. We'll start by looking at the conformation of the 3-membered ring, that of cyclopropane. And this is the molecular model for cyclopropane. And then, as you can see, we have these 3 carbon atoms that have formed a ring. 3 points define a plane. So as a result, these 3 carbons of cyclopropane are in the same plane. They cannot be in different planes. As a result, As a result of this, cyclopropane is like an equilateral triangle. And since it is like an equilateral triangle, the bond angle in here is 60 degrees. It is 60 degrees. As an sp3 hybridized carbon, the bond angle should have been 109.5 degrees. It has been compressed from 109.5 degrees to 60 degrees by about 49.5 degrees. The bond angle is compressed. So cyclopropane is unstable because of angle strain, because of the compression of the bond angle by 49.5 degrees from the ideal bond angle of an sp3 hybridized carbon of 109.5 degrees. There is nothing cyclopropane can do to change this situation. There is no way the bond angle of cyclopropane is going to be different from 60 degrees. It is off by 49.5 degrees from the ideal 109.5 degrees. It is very compressed. It is very, very strained. This is, as you shall see, the most strained angle of all the cycloalkanes. So one of the reasons cyclopropane is unstable is because of angle strain. The other reason why cyclopropane is unstable is because of torsional strain. As you can see, these hydrogen eclipses this one eclipses this one eclipses this one. The ones on top, they eclipse each other. This one eclipses this one eclipses this one. There is nothing cyclopropane is going to do because all the three carbons, they must be in the same plane. This one can only face each other, eclipsed. The top three hydrogens are eclipsed with each other. The same to the bottom hydrogen, they are all eclipsed. So these hydrogen and these hydrogens are eclipsed. As a result of that, there is going to be electrostatic repulsion between the electrons of this carbon-hydrogen bond and this carbon-hydrogen bond. Of course, this one eclipses this one eclipses this one. These ones have eclipsed each other. The same to the lower one. This one has eclipsed this one has eclipsed this one has eclipsed this one. They have all eclipsed each other like that. As a result, there is a lot of torsional strain that cannot be avoided. There is no other form cyclopropane can adopt as a result of rotation of its carbon-carbon bond. All of them, all the carbons are going to be in the same plane. The bond angle is going to be 60 degrees. All the six hydrogens are going to be strained, torsional strained, as a result of eclipsing of all the six hydrogens. If you look closely, you will see that even bonds, even in this model, these bonds are bent almost to the point of breaking. There's a lot of angle strain in the formation of cyclopropane. When the open chain, which is free with a bond angle of 109.5 degrees, that can adopt staggered conformation, when it forms a ring like this, it has brought a lot of strain to the ring by reducing the bond angle from the ideal 109.5 degrees to 60 degrees, by causing eclipsing of all the six hydrogens. As a result, a lot of torsional strain Because of this, because of combination of angle strain and torsional strain that cannot be avoided at all, cyclopropane is the least stable of all the cycloalkanes. All the 6 hydrogens are eclipsed and the bond angle is 60 degrees. As the result of torsional and angle strain, cyclopropane is very, very unstable. Let me just show you and demonstrate to you how compressed this angle really is. The 3 carbons of cyclopropane are these ones, and 3 points, this one, that one, and this one, 3 points define a plane. As a result, all the 3 carbons are in the same plane. Since they are in the same plane, this bond angle can only be 60 degrees. It can only be 60 degrees. It was supposed to be, as an sp3 hybridized carbon, the bond angle was supposed to be this much, 109.5 degrees. That's not possible. As a result, the bond angle of the ideal 109.5 degrees is compressed by this much, by about 49.5 degrees. The angle is very much compressed. And as we shall see, as we can see, such type of orbital overlap is not effective. So, as a result of this angle compression, this would make cyclopropane to have high energy, unstable, and very reactive. And then this instability is said to be caused due to angle strain. Let me further demonstrate and show you how much the angle is compressed and bent to the point of breaking. The ideal bond angle for sp3 hybridized carbons is 109.5 degrees. The orbitals of this carbon and the orbital of this carbon have overlapped head-on to form this particular sigma bond, the same to this sigma bond. They have overlapped straight like this. What does it really mean to reduce this bond angle to 60 degrees? In order for this bond angle to be reduced to 60 degrees, these orbitals have to bend. They have to bend. That's the only way. They have to compress in order to form cyclopropane. So the angle, when it's reduced from 109.5 degrees to 60 degrees, it will force the orbitals, these sp3 hybridized orbitals, to bend like this. That's the only way we can have an angle of 60 degrees. Then, as you can see, the nucleus of one is here, the nucleus of the other is here. If you draw a line that join the two nuclei, the two carbons, you will see most of the electrons of the bond are above the nuclear axis. They are not under the direct influence of the nucleus. So the force of attraction the nucleus has for the electrons is minimum, while in the case of an ideal orbital overlap of an sp3 hybridized orbital, the electrons lie across the nuclear axis. So the nucleus has a very strong attraction for these electrons. As a result, these bonds are very, very strong. But in the case of cyclopropane, the electrons of the bond, they lie above the nuclear axis. As a result, they are weak. They are bent to the point of breaking. In fact, the way the orbitals have overlapped in cyclopropane is like a banana. So that's why they are called banana bonds. bent like bananas, bent like bananas, where the electrons of the sp3 hybrid orbitals lie above the nuclear axis. They are not under the direct influence of the nucleus. As a result, this bond that holds cyclopropane molecules, the sigma bond that hold cyclopropane molecules in the ring, is very, very weak. They are very unstable. That's why cyclopropanes usually undergo ring opening reaction to relieve the strain. Rather than being strained like this, they can easily undergo a chemical reaction that breaks this weak bond like this, so that they get relieved of the strain. So they undergo ring opening reactions very easily. So now let's look at the next member of the cycloalkanes, the cyclobutane. Now, in cyclobutane, if cyclobutane was planar, that means if all the 4 carbons are in the same plane, cyclopropane will be like a square. It will be a square that has got 2 hydrogens here, 2 hydrogens here, 2 hydrogens here, and 2 hydrogens here. As a result, since it's a square, the bond angle will be 90 degrees, 90 degree, 90 degree, 90 degree. That's how it's going to be. And then since it is planar, this one eclipses this one eclipses this one eclipses this one eclipses all the hydrogens on the neighboring carbons on the top side, as well as the lower side, are eclipsed. Bond angle of 90 degree, different from the ideal 109.5 degrees. Then all the 8 hydrogens are eclipsed. So if you take the planar cyclobutane, it will have all its 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, all of them being eclipsed, and this bond angle will be 90 degrees. As a result, cyclobutane is unstable, one, because of the angle strain from the ideal 109.5. Now this one is compressed to 90 degrees. And the other reason why cyclobutane, the planar cyclobutane, is unstable is because of the torsional strain. All the 8 hydrogens eclipse each other. There's going to be torsional strain. But unlike cyclopropane, cyclobutane can do something about it, because it is not a must that these 4 carbons be in the same plane. So cyclobutane can pucker as a result of rotation of its carbon-carbon single bond that will allow it to relieve some of strains the ring is experiencing. So what it can do, it will allow this one of the carbons to come out of plane like this. It comes out of plane. So these 3, this one, that one, and this one, these ones are in the same plane, but this one is out of plane. So now when that happens, it is possible that if you look at it like this, these hydrogens, these 2 hydrogens, since they were in the same plane in the planar cyclobutane, they were eclipsing each other. As you can see, somehow some of the eclipsing is relieved. The electrostatic repulsion between the electrons of this bond and this bond somehow is minimized, is lowered. It's not completely eliminated, it is lowered. The same to this one, between this one and this one. Okay, so by adopting this conformation, a 3-dimensional conformation, cyclobutane has managed to relieve some of the strain the ring is experiencing. So cyclobutane is not a planar molecule. It is a molecule like this, where one of the carbons is lifted up by 25 degrees. So it's planar like this. Then any of the carbons comes out of plane like that, or any of this one like that, etc. All the same, out of plane by about 25 degrees. When that happens, some of the torsional strain is relieved, making this packed form of cyclobutane more stable than the planar. So cyclobutane is not a planar molecule. It is a molecule that has such a structure. So in this structure, some of the torsional strain is relieved. The torsional strain that was between this hydrogen and this hydrogen, between this hydrogen and this hydrogen, is somehow relieved. But unfortunately, this one and this one, this one and this one, they are still in the same plane. They experience some torsional strain, but somehow some of the torsional strain is relieved. Unfortunately, as it adopts this three-dimensional packed conformation, its bond angle reduced from 90 degrees to 88. In the packed conformation, the bond angle is 88 degrees. So this results in an increased angle strain, but decreased torsional strain. As a result, the ring has, as a result of relief of torsional strain, has very much compensated the instability that came to the molecule as a result of reduction of its bond angle from 90 degree to 88, going away from the ideal 109.5 degrees. So planar cyclobutane does not exist. Cyclobutane does not exist as a planar molecule. It is a bent molecule like this with three-dimensional structure. So cyclic molecules can assume non-planar conformations to minimize angle strain and torsional strain by ring puckering. This was not available for cyclopropane. Since 3 points define a plane, it cannot become non-planar. But 4 points, they are not necessarily in the same plane. So as a result, cyclobutane does not have to be planar. It adopts a non-planar conformation, and the reason why it is doing this is to minimize angle strain and torsional strain. As you have seen in the case of cyclobutane, when it packed and adopted this non-planar conformation, its bond angle went further away from the ideal 109.5. It reduced by 2 degrees from 90 to 88. But this instability as a result of reduction in its bond angle is very much compensated as a result of the torsional relief it managed to achieve as a result of puckering. The torsional strain in here is somehow relieved. The torsional strain here is also somehow relieved. So the torsional strains, if you look at the molecule like this, you will see that this one and this one are not facing each other. They are not eclipsing each other. The same, this one to this one. There is some kind of torsional relief. These ones are not quite eclipsed. There is some kind of torsion strain relief that has made the molecule, the packed non-planar cyclobutane, to be more stable than the planar. So cyclobutane is a non-planar molecule in which one of the carbons is out of plane by about 25 degrees. Of course, it is possible when you do that, like here, you can take this carbon to be out of plane, like this. It's also possible you can take this other one to be out of plane, like that. So as a result, we have two conformations of cyclobutane, one of them being this one, the other one being the other one. And then these two conformations are in equilibrium with each other. So cyclobutane, it consists of two packed conformations which are in rapid equilibrium. This conformation and this other conformation. This one, where these ones are up, and then this one, where the same are down. So like this, like that, like this, like that. These conformations are in equilibrium with each other. One conformer goes to the other conformer rapidly. A rapid equilibrium is established between them, like that. Then this conformation of cyclobutane is called butterfly conformation. As you can see, this is like flying, like a butterfly flying. In the packed conformations of cyclobutane, there are two types of hydrogens. The ones shown in red, the 4 hydrogens shown in red, and the other 4 hydrogens that are shown in green. In this packed conformation, you will see two different types of hydrogens. The ones I'm holding and the other ones that are across the equator of the ring. Two types of hydrogens. These hydrogens, the ones I am touching, are axial hydrogens, because these hydrogens, they are parallel to the ring axis. If you have an axis that goes like this, these two hydrogens as well as these hydrogens will be parallel to it. They will be parallel to the axis that passes through the ring, like that. These ones are called axial, while the others are called equatorial. So we have two types of hydrogens in the butterfly conformer of cyclobutane. Then as this ring flips like this, what happens to this substituent? So to demonstrate this so that we can easily see what is happening, let me label the way I have done in here. Let me label these equatorial hydrogens green. Let me replace these equatorial hydrogens with green hydrogens, so that as the ring flips, we see what happens to the substituents that were axial and equatorial. Okay, let's see what happens. So what I'm going to do is I'm going to replace, so this is the envelope conformation. These two are axial and the other ones are equatorial. So let me replace these ones with a green hydrogen. Okay, so as you can see, we have these ones, the white ones that are facing straight up or straight down, and then these other ones, the green ones that are across the equator of the ring at a certain angle, up like this or down, up, down like that. So when the ring flips, what happens to this substituent? So let's flip it the other way. So from here, let's do this. Now you see, when that happens, the green hydrogens that were equatorial now, they are axial. So as the ring flips like this, as the ring flips like this, the equatorial hydrogens become axial, the axial hydrogens become equatorial. Let us now see the conformations of cyclopentane. So if cyclopentane was planar, just like a regular pentagon is, these 5 carbons will be in the same plane. These 5 carbons, 1, 2, 3, 4, 5, all the 5 carbons will be in the same plane. So since this is like a regular pentagon, the bond angle, as we have seen, will be 108 degrees, closer to the ideal 109.5 degree of sp3 hybridized carbons. 108. So there is no much angle strain in the planar conformation of cyclopentane. However, in the planar conformation, since all the 5 carbons are in the same plane, the hydrogens eclipse each other. This hydrogen eclipse this one eclipse this one eclipse this one eclipse this one. All of them eclipse each other. The hydrogens above the ring and the hydrogens below the ring, all of them eclipse each other. As a result, all the 10 hydrogens of the planar cyclopentane are eclipsed, and as a result, cyclopentane suffers a lot of torsional strain in its planar conformation. So, in the planar conformation of cyclopentane, since all the carbons are in the same plane, this bond angle 108 degrees, closer to the ideal 109.5, almost no angle strain. However, in this planar conformation, all the hydrogens are eclipsing each other. This one eclipses this one eclipses this one eclipses this one, this one eclipses this one. Even the ones at the bottom, they all eclipse each other. So in the planar cyclopentane, all the 10 hydrogens are eclipsed and the bond angle is 108 degrees. As a result of the eclipsing of all its 10 hydrogens, cyclopentane suffers from torsional strain. The ring is unstable. The ring is strained. So, in order to relieve the torsional strain, cyclopentane can adopt a packed conformation where one of the carbon can come out of plane like this, like that. So when it comes out of plane like this, you will see that these 4 carbons remain in the same plane. It is only this one that has come out of plane. You remember in the planar conformation, if you look at this one, this and this were totally eclipsing each other, and this were eclipsing totally. This one eclipses this one eclipses this one totally. What happens when it goes to its packed conformation? By lifting this carbon out of plane like this. So watch what happens to these substituents. So if I lift this one up like that, you will see this one and this hydrogen, they are no more eclipsing each other. This one and this one are not eclipsing each other. This one is not eclipsing this one. This one is not eclipsing this one. As a result, the torsional strain across the hydrogens of this carbon-carbon bond is relieved. Across this, the torsional strain that was in here as well as there are relieved. Of course, there will still be torsional strain between these two hydrogens, between this hydrogen and this one, between this one and this one, because these four are in the same plane. But because of the relief of torsional strain across some of the carbon-carbon bonds, as a result of the relief of the torsional strain across some of these carbon-carbon bonds, the packed cyclopentane is stable, much more stable than the planar cyclopentane. So the packed three-dimensional structure cyclopentane will adopt as a result of rotation across its carbon-carbon single bond by lifting this carbon up, like that is this one. And then this conformation of cyclopentane is called the envelope conformation. You remember for cyclobutane, the conformation was a butterfly. It was like a butterfly that has folded and expanded its wings. But this one looks like an envelope. Let me demonstrate to you using an envelope. This is an envelope, isn't it? Now, what has happened? One of the carbon goes to the flap of the envelope. One of the carbon will be here. Of course, the other carbons, one of them will be here, the other one will be here, one will be here, the other one will be here. All these four carbons, the four carbons of the cyclopentane will be in the same plane, but one of them will be out of plane like the flap of an envelope. So this is called the envelope conformation, and cyclopentane will adopt this envelope conformation because as a result of going to the envelope conformation, the torsional strain across here is relieved. So no torsional strain in here. Of course, there will be some torsional strain here. All the same, compared to the planar cyclopentane, which has all its hydrogens eclipsed, where it suffers torsional strain across all the carbon-hydrogen bonds. In the case of the envelope conformation of cyclopentane, it is only some of them that suffer torsional strain. There is some kind of relief of torsional strain. So as a result, the envelope conformation is more stable than the planar conformation. Of course, this is much more stable than this. So cyclopentane does not exist as a planar molecule. It has got this three-dimensional structure where one of the carbons of the cyclopentane, any of the carbons coming out of plane like the flap of an envelope. Unfortunately, when this happened, when it went from the planar conformation to the envelope conformation, the bond angle reduced from 108 degrees to 105. So in the envelope conformation, the four carbons, this one, that one, this one, 1, 2, 3, 4, 1, 2, 3, 4, they are in the same plane. The fifth one is out of plane like the flap of an envelope, sort of like the flap of an envelope. The number of eclipsed hydrogens is reduced. These ones are no more eclipsed at the expense of angle strain. this angle is a bit strained compared to this, but the torsional strain relief the molecule has gained as a result of going to the envelope conformation has outweighed the angle strain the molecule experienced as a result of reducing its bond angle from 108 degree to 105 degrees. So cyclopentane has an envelope conformation. It is like an envelope. So in cyclopentane, when it is planar, all the carbons are in the same plane. As a result, the bond angle will be 108, like a regular pentagon. Then all the 10 hydrogens, the ones above the ring and the ones below the ring, will be eclipsing each other. It's going to suffer a lot of torsional strain. So when it adopts its Packard three-dimensional structure and adopt a shape like that of an envelope, it's managed to remove the torsional strain. Some of the torsional strain across here is reduced. As a result, it becomes stable, despite the fact that the bond angle reduced from 108, which is closer to the ideal 109.5, it reduced to 105. The angle strain increased, but the instability that came as a result of a strain of the angle is very much compensated by the relief of torsional strain. Therefore, the envelope conformation is more stable than the planar conformation. So, as a result, cyclopentane does not exist as a planar molecule, but as an envelope, where all the 5 carbons are not in the same plane. These 4 carbons are in the same plane, while this one is out. So it is possible that when it goes to the envelope conformation, any of the carbons can come out of plane. This one can come out of plane, or that one can come out of plane. This one can come out of plane, or this one can come out of plane. So it can have this envelope conformation where this carbon has come out of plane, or it can have this other conformation where this one has come out of plane. So it flips between this conformation and this conformation. This conformation and this conformation are always in equilibrium with each other. So the envelope conformation undergoes a rapid conformational change in which the carbon at the envelope alternates. This one can come up, or this one can come up, or that one can come up. Any of them can come up. So as a result, we have a rapid conformational change in the envelope conformation. So these conformations of cyclopentane, where this one is up, in this case, or the other one is up and the others are in the same plane, are always in equilibrium. So as we have seen, the conformers, the stable conformers, even for cyclobutane, they undergo conformational change, rapid conformational change, and these conformations are at equilibrium with each other. The same to the cyclopentane. So now, this is a case where we have all the substituents on the carbon being the same. If at least one of them was different, if this one was different, suppose this one was a CH3 while the rest of them being hydrogen, which of them is going to go to the flap of the envelope? Which one of the substituent will go out of plane? Is it the one that has got this CH3, the bulky substituent, or is it the ones that have the hydrogen? In order to do this, we need to determine the energies of the various conformation and determine the factors that make one particular conformer unstable compared to the other. So, suppose the different carbon atoms in the ring are non-identical. That is, have different substituent. How do we know which carbon atom in cyclopentane will pucker? Which of the carbons in the cyclopentane will go out of plane? Okay, I want you to think about this, and then as we go along, we'll see, especially in the case of cyclohexane, this is very, very important. So to summarize what we have learned about the conformation and stabilities of the first three cycloalkanes, the cyclopropanes, the cyclobutanes, and the cyclopentanes. As we have seen, cyclopropane is a planar molecule because 3 points define a plane. As a result of that, the bond angle is 60 degrees. It is compressed by 49.5 degrees from the ideal 109.5 degrees. As a result of that, cyclopropane suffers a lot of angle strain. The other thing we saw in the case of cyclopropane, since the conformation of cyclopropane cannot change as a result of rotation across the carbon-carbon single bond, since all of them, all the three carbons have to be in the same plane, this hydrogen and this hydrogen, this hydrogen and this hydrogen, all these on top and the ones below are eclipsed with one another. As a result, there is a lot of torsional strain in cyclopropane. So the reason why cyclopropane is unstable is because of very severe angle strain and severe torsional strain, and there is nothing cyclopropane can do about it. It has to live with it. That's why it is very, very unstable. The most unstable of all the rings is the three-membered rings. The three-membered rings, because of the strain in the ring, they usually undergo ring opening reactions in order to relieve the strain in the ring. The second member of the cycloalkanes is the cyclobutane. Now, if cyclobutane is planar, it will have a bond angle of 90 degrees and all its 8 hydrogens will eclipse with each other and the bond angle will be 90 degrees, far from the ideal 109.5. But for cyclobutane, unlike the cyclopropane, it can adopt a three-dimensional structure through puckering that will allow it to offset some of the strain in the ring. This it does so by taking one of the carbons of the ring out of plane by about 25 degrees, as we have seen. So when it does so, it has managed to relieve some of the torsional strain, some relief of, not completely, but some relief of torsional strain. As we have seen, when it adopts this butterfly conformation, the bond angle reduces from 90 to 88. The angle becomes a bit more strained than the planar. But this is, however, very much compensated by the relief it has gotten as a result of relief of some of the torsional strain. However, cyclobutane is still unstable, but it is more stable than cyclopropane. That's why cyclobutane 4-membered rings are not very common in nature. Third type of ring we have looked at is the cyclopentane ring. As we've discussed, if cyclopentane was planar, the bond angle will be 108 degrees, closer to the ideal bond angle of 109.5 degrees. In the planar cyclopentane, there is no much angle strain. However, in the planar, all the 10 hydrogens, the 5 on top and the other 5 hydrogens at the bottom, they are all eclipsing each other. As a result, there is a lot of torsional strain. All the 10 hydrogens under torsional strain. That will make this planar conformer of cyclopentane to be very unstable, despite the fact that its bond angle is closer to the ideal 109.5 degrees. It is very, very unstable as a result of torsional strain. So it will pucker. So when it puckers, as we've discussed, it puckers and adopt minimum energy conformation for a combination of 3 reasons: to get relief of angle strain, torsional strain, and steric strain. And then it is a compensation between these. It is the weighted average of this that's going to determine how stable a particular conformer is. So in order to get rid of the torsional strain, cyclopentane adopt this envelope conformation. And then in the envelope conformation, you see here this one is facing up while this one is facing down. They are staggered, and then these ones and this one are very far apart from each other as possible. So it has managed to get rid of all the torsional strain across these bonds, but these ones there's still torsional strain across this. This one is eclipsed with this one is eclipsed with this one. Some relief of torsional strain, total relief of torsional strain across this. And then when it adopts this envelope conformation, as we have seen, the bond angle reduced from 108 to 105 degrees. Despite that, the envelope conformer, the packet conformer of cyclopentane, is more stable than the planar conformation. So in terms of stability between the 3 cycloalkanes, cyclopentane is the most stable because one, its bond angle is 105, closer to the ideal 109.5 degrees. For cyclobutane, it is 88 degrees. For cyclopropane, it is 60 degrees. So cyclopentane has the least angle strain. That's why it is stable. In addition, in terms of torsional strain, in the case of cyclopropane, all the carbon hydrogens are strained. There is a lot of torsional strain. Some of it was relieved in the case of cyclobutane. But in the case of cyclopentane, at least on the carbon that has gone out of plane and the hydrogens on its neighboring carbons, it was possible to totally eliminate the torsional strain. That's why it is the most stable. Now we'll see the conformations of cyclohexane and see the reason why cyclohexane is the most stable ring. Let us now look at the conformations of cyclohexane. So, if cyclohexane is planar as a regular hexagon, where all the 6 carbons are in the same plane, as we have discussed this bond angle will be 120 degrees, way above 109.5 degrees. As a result of that, the planar cyclohexane suffers from a lot of angle strain. The other thing, in the case of the planar cyclohexane, all the 6 hydrogens on top of the ring, this one eclipses 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 this eclipses this. As a result, all the 6 hydrogens on top of the ring have eclipsed each other. The same to the hydrogens at the bottom of the ring. All the 12 hydrogens in the planar cyclohexane have eclipsed each other. Therefore, the planar cyclohexane is unstable as a result of severe angle strain and torsional strain. So, in the planar cyclohexane, where all the carbons are in the same plane, since it is shaped like a regular hexagon, these bond angles will be 120 degrees, very much above the ideal 109.5 degrees. It will be suffering from a lot of angle strain. In addition to that, since it is planar, this hydrogen faces directly this one faces this one, they face each other like this. This one faces this one faces this one faces this one faces this faces that, this one faces that. The same to the hydrogens below the ring. All the 12 hydrogens are eclipsing each other like this. As a result, there is going to be a lot of electrostatic repulsion between the electrons of the carbon-hydrogen bonds on neighboring carbon atoms. All 12 of them are going to have electrostatic repulsive forces, making the planar cyclohexane to be very, very unstable. So the planar cyclohexane is unstable as a result of the fact that all the 12 hydrogens are eclipsed and the bond angle is 120 degrees. As a result, this planar conformer of cyclohexane is very, very unstable. As a result, cyclohexane, just like cyclobutane and cyclopentane, can adopt a packed 3-dimensional conformation that will allow it to relieve its angle and torsional strain. So, remember, in the case of cyclopentane, what happened was one of the carbons came out of plane to allow some relief on the ring. But in the case of cyclohexane, 2 of the carbons can come out of plane as it packers and becomes stable. It is possible that this carbon can come out of plane and goes up like that. And then this one can come down like that. This one goes up while the other one comes down. Let me just demonstrate this using this regular hexagon. So in here, since this is planar, all the 6 carbons here are in the same plane. Of course, we have 2 hydrogens here, 2 hydrogens here, 2 hydrogens, 2 hydrogens, 2 hydrogens on each of the carbons. Let's assume they are there. So since this one will cause the bond angle to be 120 degrees and cause all the 12 hydrogens to eclipse with each other, cyclohexane adopt a three-dimensional conformation by rotation across its carbon-carbon single bond. Then how it does it is by allowing this carbon to come out of plane and go up like this. This is what has happened in the case of cyclopentane. Only one of the carbon managed to come out of plane. But in the case of cyclohexane, this one and the carbon that is directly opposite to it will come out of plane. This one will go out of plane by going up, while this one, it will go out of plane by going down, by folding down like this. Okay, it will adopt such a conformation, where this one is out of plane going up, the other carbon is out of plane by going down. However, this carbon, this carbon, this carbon, and this carbon, the four carbons will remain in the same plane. So this conformation, it can adopt by taking this one up and the other one down. So when it packets by rotation across its carbon-carbon single bond, it will adopt this conformation. This is the most stable conformer of cyclohexane. This conformer is called the chair conformer. As I will show you in a short while, this actually looks like a chair. Even if you look at this, if you look at this simple model, you will see someone can sit here and rest his or her back here, and then the legs will come like this. So this is like a chair, and I will demonstrate to you this is indeed a chair conformer. So let me show you using this model. So what's going to happen from the planar as it goes to the chair conformer? What is going to happen? The carbons that are opposite to each other, this one and this one, will go out of plane in different directions. This one can go up like this, and then the one directly opposite to it will go down like that, and then adopt this conformation. And this is the chair conformer of cyclohexane. I want us to analyze how the hydrogens on the neighboring carbons are arranged to each other. I want us to see this. Like, let's concentrate on these two carbons. As you can see, the hydrogen on this carbon is facing up like this, while the hydrogen on this other carbon is facing down. This one is facing up, this one is facing down, totally eliminating the torsional strain. Again, if you look at this one and this one, which are on neighboring carbons, they are as far away from each other as possible, totally eliminating the torsional strain. This it does across all the carbons. You come here, this one is up, this one is down, this one is like this, this one is up like that. Let's come here, Between the two, this one is up, this one is down. This one is like this one is like that, as far away from each other as possible, eliminating the torsional strain. The same in here, up, down. This one's further away, up, down, up, down, down, up, up, down. So when cyclohexane adopted its chair conformation, it managed to eliminate all the torsional strain. As a result of that, when cyclohexane formed a ring, it did not suffer any type of torsional strain, none whatsoever. You remember, as we were progressing from cyclopropane to cyclobutane and then to cyclopentane, we were progressively seeing some relief of torsional strain. In none of the cases, the torsional strain were totally eliminated across all the carbon-carbon single bonds. But in the case of cyclohexane, all the torsional strains were eliminated by adopting this chair conformer. As you can see, if you look at this carbon and this carbon, this one is facing up like that, while the other one is facing down. So the hydrogens that were facing each other like this, eclipsing each other, and as a result going through a lot of electrostatic repulsive force by rotation across its carbon-carbon single bond, cyclohexane managed to totally and completely eliminate the torsional strain. This one facing up while the other one is facing down. So cyclohexane in its chair conformer does not suffer from any kind of torsional strain, relieved of torsional strain. Managed to completely eliminate the torsional strain. The other thing it has managed to achieve is eliminate all the angle strain. In the planar conformer, the bond angle was 120 degrees. But by adopting this chair conformer, the bond angle became 109.5 degrees. The ideal bond angle for an sp3 hybridized carbon. So in the chair conformer, this bond angles, this one, that one, all the bond angles are 109.5 degrees. The sp3 hybridized orbitals of cyclohexane have overlapped the way they were supposed to overlap, without any bending, without expanding or compressing, with the right angle. So the chair conformer is very stable, as it has managed to totally eliminate the torsional as well as the angle strain. So all the 12 hydrogens are staggered, and the bond angle is 109.5 degrees. As the result, cyclohexane is very, very stable. It does not exist like this. Whenever you are trying to discuss the chemistry of cyclohexane, if you write it as a planar cyclohexane, it's not going to represent its chemistry. You should write it as a chair, and then using the chair, you can explain most of the chemistry, the chemical properties of cyclohexane. Now, even consistent with the experimental data from the heat of combustion, which has shown us cyclohexane is the cycloalkane that has the least energy per CH2, the most stable. The same energy as an open chain alkane, as stable as an open chain alkane. By forming a ring, it did not become strained. formation of a ring cyclizing like this can be constraining, making the situation very unstable. We prefer, relaxed like this. When something cyclizes like this, falls like this, it becomes constrained. It becomes unstable. Other than this, but by forming a ring like this, cyclohexane did not suffer from any kind of strain. It is a very stable cycloalkane, as stable as the open chain. So of all the cycloalkanes, the most stable and the most abundant ring you find is cyclohexane. It is very easy to synthesize a cyclohexane ring in the laboratory as well as in biological system in nature. That's why if you go through books of organic chemistry and go and look at all the different rings that are there, you will see the most abundant ring is a 6-member ring because of its stability. Next to the 6-member ring, the most abundant one is a 5-member ring. 4-membered ring and 3-membered ring are very rare because of their instability. So let me further demonstrate to you. This is indeed a chair conformer. From the way it looks, you may not see that this is a chair. Let me demonstrate to you so that you are convinced this is actually a chair. I've managed to convince you that packed conformation of cyclobutane is butterfly and that of cyclopentane is envelope. Let me convince you the most stable conformer of cyclohexane looks like a chair. Let's look at this chair, this lazy chair. It is possible to put the 4 carbons, one here, the other one here, the other one there, another one there, and the 5th one here, and the 6th carbon in here of the chair conformer of cyclohexane, like that. This 1, 2, 3, 4. These are the ones that are in the same plane. And then this one is up, the other one is down. You might think that this is really not a comfortable chair. Let me show you how comfortable it is. You can, like this lady, she's enjoying herself sunbathing on the beach by sitting on a cyclohexane chair. So this 1, 2, 3, 4, these 4 are the 4 carbons that are in the same plane. And then this one is up where she's resting her back, and this one where she's resting her leg. And as she's sitting there, she's saying hi to this young man who is also seated on a cyclohexane chair. So let me just give you another example, just as a joke. When ordinary people see this icon, they will say this is an icon for a messenger. This is how normal people see this icon. They see it as a messenger. How about chemists? How chemists see this is different. Chemists see this as the chair conformer of cyclohexane. So I hope by now you are convinced indeed the most stable conformer of cyclohexane is the chair conformer. This is adopted by taking one of the carbons out of plane and the other one right opposite to it below the plane, like that, up, the other one down. This chair conformer is achieved. Of course, in addition to the chair conformer, there are other conformers of the cyclohexane. These are called the boat conformer, the half boat conformer, the twist boat conformer, Maybe as you read, you might come across this and you might decide and determine which one of these more stable than the other. But the most stable one is the chair conformer. Now, in the chair conformer, you see these hydrogens on neighboring carbon. This one is facing up. If you look at it like this one is facing up while this one is facing down. And if you look at this one is like this at an angle like this, while this one is on the other side, the same to this one. If you look at them like that, you'll see this one and this one are separated by 180 degrees, as far away from each other as possible. And this one similarly, they are separated by 60 degrees. This one and this one are separated by 60. This one and this one are separated by 60. This one and this one are separated by 60. This one with this one is separated by 60 degrees, etc. The furthest they can be. As a result, in the chair conformer, all the 12 hydrogens are staggered. They do not suffer from any type of torsional strain. Now let's further investigate the chair conformer. You remember in the case of the cyclobutane, I showed you in the cyclobutane there are two types of hydrogens. Axial hydrogens and equatorial hydrogens. The ones I'm touching are axial, the other four are equatorial, which lie across the equator of the ring. And then, as we discussed, as the ring flips from one conformer to the other conformer like this, axial becomes equatorial, equatorial becomes axial. So what I want us to do is investigate similarly how the hydrogens of cyclohexane that are on the same carbon as well as on the neighboring carbon, how they are related to each other. So let's investigate this. So this explains the concept pictorially, but let me demonstrate this one using a model. So in the chair conformer, this one is up while this one is down. This one is down, this one is completely up. Like that. This is a chair conformer. As you can see, I can touch and hold these hydrogens, these 6 hydrogens, like that. These ones are either facing straight up or straight down. Straight up or straight down. If you have a ring axis like this, these ones will be parallel to it, facing either up or down. These ones are axial substituent or axial hydrogens. In this case, these ones are axials. And then the ones I'm not touching, the other 6 are equatorial hydrogens because they lie across the equator of the ring. So we have 2 distinct types of hydrogens in the chair conformer of cyclohexane: axial and equatorial. 6 of them are axial while the other 6 are equatorial. Of course, cyclohexane, just like cyclobutane and cyclopentane, it undergoes flipping of the ring by taking this one up and this one down. This is 1. It is possible, of course, nothing will stop it from taking this one down and then this one up. Whichever case, both of them are chair. You have this one, and then you have the other one. These two conformers are in equilibrium with each other. This one, where this one is up and the other one is down, and this other one, where this one is down while this one is up. This one is completely down, this one is up. These ones are in equilibrium with each other. The ring flips from one form to the other. Now, what happens to the axial and equatorial hydrogens as the ring flips? You remember, in the case of cyclobutane, I demonstrate to you as the ring flips, the axial substituents were becoming equatorial, the equatorial becoming axial. The flipping of the ring, that rapid equilibrium between the two flipped from the ring, is a natural phenomena, is a phenomena that cannot be avoided. The two exist in equilibrium with each other. There is going to be an equilibrium. So what happens when it equilibrates between the two conformers to the hydrogens, to the axial and equatorial hydrogens? To demonstrate this, let me replace the equatorial hydrogens, these ones which are white in here, with green hydrogens. So let me have all the equatorial hydrogens green and the axial hydrogens white the way they are. Let's see what happens. So let me just remove these ones and replace them. So in here, as you can see, the equatorial hydrogens are green while the axial hydrogens are white. These ones are facing straight up or straight down. That's what an axial substituent is. A substituent that faces straight up or straight down, not at an angle. Okay, if I put a line like this, you will see that these ones are facing straight up and the other ones are facing straight down, straight up or straight down. This is the chair conformer. These ones, the ones I'm touching, are axial while the other ones are equatorial. Now let's flip the ring. What happens to this substituent? Will the axial, the hydrogens in white, become equatorial? Will the equatorial hydrogens, the ones shown in green, will they become axial? Let's do this. So in this chair conformer, this one was up while this one is down. So let me bring this one down, completely down, and then the one opposite to it completely up. Yes. Now you see these green hydrogens, they were equatorial, now they have become axial. The white hydrogens, they were axial, now they are now equatorial. So as the ring flips between the two forms, between this one and this one, where there is a lot of equilibrium, rapid equilibrium, the axial hydrogens become equatorial, the equatorial hydrogens become axial. I want us to be serious about this, as this has a lot of implication for the stability of cyclohexanes as a chair conformer. We'll have more discussion on this. But what I want you to know for now is the establishment of equilibrium between the two forms is not something that can be avoided. It is spontaneous. It happens. Both conformers are chair, except that what was axial in one chair, as the ring flips, becomes equatorial. What was equatorial in one conformer, it becomes axial in the flipped conformer. That's very important. And then the other thing I want us to learn before we go any further is how the axial and equatorial hydrogens are related to each other compared to the ring, how they are related to each other. Let us see. Now, if you look at, let's first look at the axial substituents. These ones, the ones I'm touching. On this carbon, we have this axial substituent, and this axial substituent is facing up, as you can see. How about the axial substituents, which are indicated in green? In what direction are they facing in relation to this? As you can see, this one is facing up, but the ones in the neighboring carbons, the axial substituent in the neighboring carbons are facing down. Facing down. Let's come this way, just to see how it is like across the ring. As you can see, this one is down, this one is up, well, this one is up. And then if you look at this one is up. The axial substituent on the neighboring carbons are in the opposite direction. Down, 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 up, up, down, up, down, up, down. That's how the axial substituents are arranged on neighboring atoms. If the axial substituent on this carbon faces up like this, the axial substituent on the neighboring carbon is facing down like that. We'll look at the significance of this in a short while. How about the orientation of the equatorial substituents? Let's just look at it. Then I want you to see this one first, this one. In which direction is this hydrogen facing in relation to this carbon? Is it facing down or is it facing up? As you can see, it is facing down. How about the equatorial substituent on the neighboring carbon? Let's first look at this one. This one, as you can see, it is facing up. This one is facing down. This one is facing up. Let's look at this one. This is facing down, but this one is facing up. So similarly, the equatorial substituents on the neighboring carbons are facing in opposite direction. Up, down, up, down, up, down, up, down. Because this is very important. Because in order for us to discuss the conformation and stability of cyclohexanes and to do conformational analysis and determine which of the conformation is the most stable, we should be able to draw the chair conformation very well. Later on, I will show you how to draw a chair. Just practice and see how good you are in drawing the chair conformer. Some of you, instead of drawing a chair, you will be drawing a butterfly or a plane, totally different. So it's very important for us to learn how to draw the chair conformer. I will show you how that is done. The other thing we should know, how the axial and the equatorial substituents are oriented. The axial substituents are facing either straight up or straight down, not at an angle, not like this or like that. They are either straight up or straight down. And then the equatorial substituents are at an angle. They could be like this, or they could be like this. They could be like that, or like this. And the substituents on neighboring carbon atoms, they face in the opposite direction of the ring. This one is facing up, but the axial substituents on the neighboring carbon are facing down. The same to the equatorial substituent. And the other thing, of course, It is very trivial, but very important to note that on the same carbon, we have these two substituents. If one of them, like this, is facing up, the other one, this is axial, the other one should face down. So when you are drawing the chair conformer of cyclohexane, and then you are indicating all the hydrogens, the axial and equatorial hydrogens, you must know how to draw them. You cannot draw a chair conformer where the substituents on the same carbon are facing the same direction. If this one, as you can see, is facing up, this one is down. Let's look at this one. This one. As you can see, this one is obviously facing down. But look at this one, the equatorial one. It is facing up. Facing up. This one is facing down. Facing up, facing down. Facing up, facing down. That's how it is. Now, you remember what I told you? In cycloalkanes, there is no much freedom of rotation as there is in the open chain alkanes. Then as a result, in cycloalkanes, we have cis and trans isomerism. So let's now identify different 1,2 substituted cyclohexanes as cis and trans by first identifying what the orientation of the substituent is, whether they are axial or equatorial. The type of the substituent, whether they are axial or equatorial, and what is their orientation relative to the ring. Are they above the ring or below the ring? That way determining whether the arrangement of the two substituents on a cyclohexane ring is cis or trans. Just look at this. So if you look at these, this is a chair conformer of cyclohexane that has got 2 methyl substituent. It is a cyclohexane that has got 2 methyl substituent. A methyl substituent here, another methyl substituent. This is a 1,2 dimethyl cyclohexane. This one is also a 1,2 dimethyl cyclohexane. Let us see whether these two are the same molecules or different molecules. In order to do that, we have to determine how their substituent, the methyl substituents, are oriented to each other relative to the ring. Then based on that, we can write them as either cis or trans. If they are both cis, since they are next to each other, since they are 1,2, in both cases 1,2, they will all be, both of them will be cis 1,2 dimethyl cyclohexane. So let's look at this one. If you look at this one, this methyl is facing up like this. So what I want you to know, there are hydrogens everywhere. For purpose of clarity, I have not shown them because we just want to focus on these methyl substituents and determine how they are related to each other. So if you look at this methyl group is facing up like this, straight up. It's not at an angle. Since it is facing straight up, this is axial. How about this one? This one is not facing straight down. Remember, if this axial on this carbon is facing up, the axial methyl substituent at this carbon, it must face down. Like this. But this is clearly an equatorial substituent because it is oriented at a certain angle. So this one is equatorial. Now, let us investigate the orientation of these two substituents in relation to the ring, whether they are in the same side of the ring or in opposite side of the ring. So as you can see, this one is facing up, while this one is also facing up. Both of them are facing up. Let us look at this one. This one is like this. It is oriented at a certain angle. It is an equatorial substituent, while this one is an axial substituent that is pointing right down. So this is equatorial, this is axial. This one is facing down. This one is also facing down. Both of them are in the same side of the ring, the way these ones are. As a result of that, the arrangement of these two methyl substituents in both rings is cis. So this is cis-1,2 dimethyl cyclohexane. You should not be surprised that these two indeed are the same. You remember what I told you, cyclohexanes always undergo ring flip. The most important thing you need to notice when cyclohexanes undergo ring flip is axial substituent become equatorial. Equatorial substituent become axial. So these two are in equilibrium with each other. So they represent the same molecule, cis-1,2 dimethyl cyclohexane. This equilibrium is something that cannot be avoided. These two are always in equilibrium. You cannot separate one from the other. You will find always as equilibrium mixture, cis-1,2 dimethyl cyclohexane. And then let's look at this one. In here, as you can see, this one is at a certain angle, while this one is also at a certain angle. Both of them are equatorial. This one is equatorial, this is also equatorial. And then when you look at this one is facing up, while this one is facing down. Straight up or straight down, not at a certain acute angle. So as a result, these ones are axial. And then if you look at the orientation of the substituents in relation to the ring, you will see that this one is facing down, while this one is facing up. Up and down in opposite direction of the ring. How about this one? This one is facing up, while this one is facing down, up and down. As a result, these two molecules are trans-1,2 dimethyl cyclohexane. Trans-1,2 dimethyl cyclohexane. Of course, you should not be surprised the fact that these are identical molecules that are in rapid equilibrium with each other as a result of flipping of the ring. Because when the ring flips, equatorial becomes axial. Equatorial becomes axial. Axial becomes equatorial. Axial becomes equatorial. These are in equilibrium with each other. Let's look at two more examples. So let's look at this one. This is a situation where the methyl groups are 1,3 related. This is position 1, this will be position 2, and then this will be position 3. 1, 2, 3. Both of them are 1,3 dimethyl cyclohexane. Are these the same molecule or different? Let us investigate. Then when you look at this one is pointing at an angle down. This is equatorial. This one is also pointing down at a certain angle, is equatorial. Equatorial, equatorial. And then these ones are facing up. This one is also facing up. Both of them, since they are facing straight up, they are axial. Of course, what I told you, when a ring flips, equatorial become axial. So these were equatorial in here. When the ring flipped, they became axial. So these two are basically the same molecule. And then if you look at this methyl and this methyl, both of them are facing up. They are in the same direction of the ring. Even here, this one faces down, this also faces down. They are in the same direction of the ring. Both of them are cis-1,3 dimethyl cyclohexane. Let's look at another example and settle this issue once and for all. Let's look at this situation. Now, this is the same 1,3 arrangement, 1, 2, 3, 1, 2, 3, but the arrangements are different. In here, this one is facing up, straight up. This is axial. This one is facing down. This is equatorial. In here, when the ring flipped, this one that was axial became equatorial, and then this one that was equatorial, it became axial, and then this one is facing up, this one is facing down in opposite direction of the ring. The same to this one is facing up, while this one is facing down in opposite direction of the ring. As a result, both of them are trans dimethyl cyclohexane.